I'm going to wrap up this first group of talks, and so I'm afraid I'm going to repeat a few things that other speakers have already said. The first being that I'm very grateful to the organisers for giving me the opportunity to be here, and the second one you will see what that is. So I'm going to be talking of gap inequalities for the Muscat problem, and it's a joint work with Konstantinos Kaparis and Latchford, who are both in the audience. So I'll try to use this gadget. So this is an introduction, which is actually a roundup of the talk to give you a flavour of what it is all about. You have already seen Muscat problem today. It's a classical problem in combinatorial optimization with loads of applications, and gap inequalities in particular is a very general class of cutting planes that were introduced. Well, they go back a little bit in the mist of time, 1996, introduced by Adolfo and Poljack. And the reason why I say in the mist of time is because since then they were quite forgotten, strangely, because they're very general. So we decided to study them just for a change. So the talk is actually based on three short papers that we've wrote over the last couple of years. The first two have already been published, the third is still work in progress. So I have three short stories to tell you. The first being how to extend gap inequalities which were introduced for the Muscat problem to a much more general class of problems, which is non-convex mixed integer quadratic programs. The second story, again a short story, is some computational complexity results related to gap inequalities. And the third is some experiments with it, with gap inequalities as cutting planes in a cutting plane scheme. Okay, so hopefully the notation is similar to the one Miguel has already introduced. Okay, so you're given a graph, here's the set of vertices, the set of edges, and so if you take a subset S of the vertices, the set of edges that have just exactly one end vertex in S and the other set that is not in S is an edge cut set, or a cut. So imagine you're also given a weight vector over the edges, so your edges are weighted, then Muscat problem calls for a cut of maximum weight. And it's an NP-hard problem in a strong sense, so no pseudo-polynomial algorithms, although it can be approximated with that ratio if the weights are non-negative. That's a very important result by Gemmels and Williamson, and it's based on STP relaxation. Right. So this is another formulation from what you have already seen with Miguel. It's based on x variables. You have a binary variable for every edge. So you have n choose 2 variables, and so it takes value 1 if the edge belongs to the cut, 0 otherwise. And this is just another way to write the triangle inequalities. And so the convex hull of these vectors, of the cut vectors, form the cut polytope, which has been studied extensively, and there are lots of valid inequalities known for it. Lots of these inequalities belong to this so-called product type. So product type inequalities. So they are defined by a vector B in Rn, and is cardinality of B as usual, and R, which is the right hand side. And then a prototype inequality will look like this. So you sum up all the edges, multiply by Bi, Bj, less than or equal some right hand side. Okay, most inequalities, lots of inequalities look like this. By the way, triangle inequalities belong to this class. For example, PSD inequalities who define the so-called elliptope, which is the feasible region for the SDP relaxation, are prototype inequalities. And they take this form. They have Bi, Bj. Again, you have the same summation over the edges, Xij, less than or equal than sigma b squared divided by 4, where sigma b is just the sum of the entries of the b vector. And from the PSD inequalities, you can derive the so-called rounded PSD inequalities. These are never facet defining. The rounded PSD inequalities are facet defining sometimes. So the idea of the rounded PSD inequalities, these are defined for every b in Rn. Okay, but if you restrict to b's that are integer, I don't know if you can see, and sigma b is odd. Okay, so then you take the square of an odd number, it's going to be odd, so it's going to be fractional, and you can round it down. So in other words, rounded PSDs are just strengthening the PSDs. And the idea of gap inequalities is to take this idea further, so try to reduce the right-hand side as much as possible, of course by keeping the inequality valid. So the question is, I don't know how to phrase it, how big this term can be, okay, the left-hand side. And in fact, if you think about it, it's a bit like solving a max cut problem where the weights of the edges, Wij's, is bi times bj. Okay? And it turns out that the best thing you can do, it may not be possible, but the best thing you can do is to have a partition where you have half of sigma b on one side. This is s. Sorry, this is a 2. And half of sigma b on the other. Okay. This partition may not be possible. Well, to know this, you have to solve the partition problem, right? This is b minus s. So you want to get as close as possible to this partition. And the definition of gap of the b vector exactly tells you the minimum difference that you can get between the sum of the entries of the elements in these two partitions. So the best you can do, if you can't do this partition, is having sigma b minus gamma b divided by 2, and here you have plus gamma b divided by 2. Okay, so gamma b is the minimum difference between these two subsets of the entries of the b vectors. So like if you have 6, 7, and 8, the best thing you can do is having 6 and 7 on one side and 8 on the other. Okay, so this is the form of the gap inequalities. You can see that what we did was just subtracting square of gamma b from this side. So this is the best thing we can do to keep the inequality valid. And in fact, gap inequalities always define proper face of cut end, always supporting, because if you have the incidence vector of a cut, in order to satisfy the gap inequality, it must be the incidence vector of a cut that has exactly that gap, otherwise it won't satisfy it. But we also know that by definition of gap, that incidence vector always exists. So gap inequalities are always defined proper faces. Okay. And this is just a hierarchy that shows you that gap inequalities are extremely general. So they generalize all these other inequalities that are all of prototype, including PSDs and rounded PSDs. Now, the downside with gap inequalities is that, as I said, computing the gap is NP hard. And in particular, testing if the gap is 0 is equivalent to the partition problem. So maybe this is the reason why they have been ignored for a while. Okay, that was the literature review. Now, about the 3 short stories. The third short story is about extending this concept of gap inequalities to non-convex mixed integer quadratic program. It is quite straightforward to extend them to the Boolean quadratic polytope, because there's a mapping between the Boolean quadratic polytope in n-1 and the cut polytope in n. Doing it for mixed integer quadratic programs is a bit more interesting, and this is just recalls you what mixed integer quadratic program looks like. So you have here's a point, you have a quadratic objective function. This Q metric is non-PSD in general, so it's non-convex. Then you have linear constraints, some continuous variables, some integer variables. And the usual trick in global optimization would be defining new variables that represent the product of the xi and xij, and then arrange these variables in a matrix. So you end up with this. So in other words, you have the Frobenius product up here in the objective function. This is nothing but a linearization, and you've moved all the complexity due to the quadratic term in these constraints. Usually, to have a tractable relaxation, you relax the integrity constraint and make this a SDP constraint. Then, of course, you can try to strengthen the relaxation using RLT or any cutting plane. So the idea is to use these new cutting planes derived from the gap inequalities. And so it is quite easy to see that you can define PSD inequalities for a mixed integer quadratic program. I'm going to write here because I don't know. Oh, here, I can erase this. So PSDs, you can, if you have alpha transpose x minus beta and you square it, this is always going to be greater than or equal than 0. So you can think of this as an extension of PSDs. Okay. This is going to be for every alpha in Rn beta, alpha beta in Rn plus 1. And you can also extend the idea of RPSDs if you say, well, if alpha, beta, and also the x are integers, some zeta, something, then alpha transpose x minus beta squared will always be greater than or equal than alpha transpose x minus beta. So that these would be the RPSDs. Now, for the gap inequalities, you can think, well, how much can I reduce this right-hand side? You have alpha transpose x minus beta. Now, this gamma, which would be the gap for the mixed integer quadratic program, can be defined as the minimum among the alpha transpose x minus beta such that x belongs to the feasible set of your mixed integer quadratic program. Okay, so you just try to find the x that minimizes this quantity. Sorry, this must be squared. Okay, so this would be the equivalent of the gap inequalities. But you can also see them that way. So these two ways are absolutely equivalent because imagine you have that disjunction. So if you multiply these two terms, then this is going to be greater than or equal than 0. And it is exactly equal to this if you think about the feasible region. In that case would be minus equal than L, greater than or equal than U. And then if you set beta to U plus L divided by 2, then the gap is this. Okay, the best thing you can do is to put x equal to L or U. Okay, and this will be the smallest gap you can get. So that's the extension to mixed integer quadratic programs. Right, so this is the second story. With the second story, we go back to max-cut. So that was about extension to mixed integer quadratic programs. This is about max-cut problem. These two results very interesting because they imply that there exist some gap inequalities with nasty coefficients. And by nasty coefficients, we mean, well, the first theorem tells you that if all the gap inequalities that are non-dominated were gap 1 inequalities, then NP would equal co-NP, which is unlikely to be. So it is likely to be that there exists a gap inequality with gap larger than 1, strictly larger than 1, which is non-dominated by other gap 1 inequalities. And also, if there exists a polynomial in N such that every gap inequality is implied by a gap inequality where the norm 1, the one norm of the B vector, is bounded by this polynomial, again, NP equal covariant P. So we expect that there are non-dominated gap inequalities with B coefficients which are not bounded by a polynomial. They're nasty. Right, this is the third result related to complexity, and as far as we know now, it is a slightly positive result. So we know that there's a separation problem for, you can define a separation problem for gap inequalities which is finite, but unfortunately it is doubly exponential. So we don't know if there's a singly exponential separation problem for gap inequalities. So far this is what we have. Okay. And then we get to the third story, which is how to use, these are computational experiments on how to use gap inequalities within a cutting plane algorithms. So what we have now is a heuristic separation algorithm for triangle inequalities, and then a heuristic separation for gap inequalities. We're not using this complicated doubly exponential algorithm, which is hopeless, so we use a heuristic one. And we also try some primal stabilization to get rid of tailing off effects. Okay, these are just technical details. And these are preliminary results. We just try to compare how good the gap inequalities were compared to the SDP relaxation. So, let me tell you, this is the average on instances taken from the Big Mac library. The first line is the average on instances with 60, 80, and 100 nodes and 50% density. And the last row, these are very dense instances with weights -1, 0, and 1. This is integrality gap with triangle inequalities. This is an integrality gap with SDP relaxation. And this is the integrality gap with gap inequalities plus triangle inequalities and some stabilization. So you can see that we're always able to beat the SDP relaxation, although sometimes it takes quite long. And yeah, we also have to figure out whether we can do any better by sparsifying the gap inequalities that we separate in order to help CPLEX to deal with these very dense LPs. And so I will conclude with some open question. One is the one I have already told you. Does there exist a singly exponential separation algorithm for gap inequality? We don't know. Second question, is the convex set defined by gap inequalities a polytope? We know it is a polytope for rounded PSD inequalities, but we don't know whether it is a polytope for gap inequality. And the third question, which is very interesting, is whether there is a gap inequalities with gap larger than 1, which induces a facet of cut n, so it's non-dominated. And yeah, as I said, we're experimental with sparsifying gap inequalities in order to speed up our cutting plane algorithm. So as usual, I finished quite early. It's typical of me, so I've got plenty of time for questions. Feel free to ask. Yes.
Can you go back to your previous slide?
Yes.
So one would suspect that the SDP with the triangle inequalities would be very good.
Mm-hmm.
Very, very good. Did you try that?
No, we just want to do something that doesn't use any SDP.
Yeah.
Just purely cutting planes. That's why we were trying. But yeah, if you could include that, it would be much better. Yeah. Any more questions? Right, so I'll see you at the dinner, and I can take up questions here at the dinner as well. So.